So today we have a talk by our Chinese friends about identities concerning integer parts. So who will be the speaker? Bohan, probably you? Wonderful, wonderful. Let us begin.
Okay, thanks for invitation. And my title here is on identities concerning integer parts. Okay. First, let the bracket are let the bracket denotes integer part, and this be the fractal part of a real number. And in 2007, Zhuravlev he studied the Fibonacci timing, and when he studied the renormalization for the map, yeah, where here tau is the golden ratio, and he found two equations, the two equations. The first is holds for all non-zero integers, and the second, in fact, is holds for all integers. And what's interesting is the inverse of the property is also true. That if the real number alpha satisfies this equation, this identity, if and only if alpha is a golden ratio, this give us a criterion of the golden ratio. And Zhukova and Shutov prove that prove the theory, and in fact they have a stronger property. That if alpha is a golden ratio, if and only if the identity holds for all Fibonacci sequence, so this then can be replaced by a Fibonacci sequence. And their proof use their proof says that alpha belongs to something like f plus 2 over f plus 2. Something like this. There may be more lemma, and this interval will converge to the golden ratio. And our paper generalizes this equality this property, and our version is if alpha satisfies some algebraic equation, alpha is a solution of, for example, if alpha is a solution of this, then if and only if the identity holds for all non-zero integers, this gives us some criterion for the algebraic integers. But we can say nothing about if we take n to some special sequence. For example, we can't take n to be a Fibonacci sequence. And what I didn't mention before, that in Schutov's paper, they use the best approximation, maybe, or you can say they use continued fraction. And in our paper, we just need equidistributions. So if we don't have some, if we don't have the equidistribution for a special sequence, we don't have the property.
So to prove a previous theorem, you need to decompose integer into Ostrovsky sum. Yes, you should use Ostrovsky numerical system.
Yes.
And you do not use numerical systems. You just use only equidistribution properties.
Yes. So our theorem is a generalization of theory 1.1, not theory 1.2.
So if L equal how do you get previous theorem? You put L and K to be equal
1.
Equal 1.
So here is alpha square minus alpha.
Then the right hand side is just 1. I see.
So it's only one solution for if it's a positive real number.
Yes.
Okay.
Okay.
Any other questions? Now I will give
Okay, we have not too many participants, so we may try to do everything clear for everybody. I think so. Don't be afraid of simple questions.
Let me give a short proof. First, if the proof of the easier part, that we assume alpha satisfies this equation for some integer m. And it's easy to say alpha L and alpha to the k are not rationals. In fact, if it's rationals, you will say this can't be true for some n. So we can first we need this property, and from this equation, it's easy to say alpha is in 1 and 2 to the 1 over k. It's should I speak more, or it's just easy computation?
Is it clear, Anton? Is it clear? Are you here?
I think yes.
Because today I am sorry. Today I have a problem. I spent all the night somewhere, and I'm afraid I need to ask. At least I need to ask a lot of questions and to think, just not to fall asleep. Okay, so if you mean that if this product alpha L times a bracket belong to the interval 1 over
to L over k.
L over k, then alpha itself belongs to the following interval.
Yes, because first we say alpha is greater than 1. Otherwise, this is.
Otherwise, it is negative. Yes.
Yes.
Okay.
Alpha is greater than 2 over L. Then this is.
Okay. Yes.
Yeah.
I'm sorry. Today it is better to be slow. Because in some sense the result is the result itself. I do not understand well where these results come from. So
Uh,
up to now, so we should be careful with very details, not to make
okay,
a
okay.
mistake, because the formality of the proof, even for simple things, is important now. So I don't know. Maybe Anton knows better where this results comes from.
No, it is strange.
Yes, yes.
Как загадка по-английски. В общем, I think that it is very nice, but very mysterious.
Yes, yes.
Let's say more about details.
I do not know. I do not know where the reason why it is true.
Okay.
This is
I
something
agree.
similar
I know
Mощевитин
different
theory.
proofs, but I cannot say that I understand.
I can say the same about Mощevitin theorem. If anybody remember it, we even have theorem about many permutations, but we didn't understand the simplest one also, not more difficult. So okay, so let me be very accurate. So everything is clear now. Everything is absolutely clear. Indeed, alpha belongs to this interval. Well, okay.
Well, so when alpha in the intervals, then alpha to the k is in one and two.
Okay. Yes.
So
Everything is okay.
It's not an integer.
Yeah. Yes. Alpha is not an integer. Yes.
No, alpha to the k is not an integer.
K is not integer.
Yeah.
Yes.
And this lemma tell us that if alpha L and alpha K are rationals, and we write it here.
Yes.
Then if one is integer, the other should be integer. How to say? If alpha to the L, one of them are not integer, then the other are not integer.
Okay.
That. So that means Q alpha k is not integer means alpha prime is not equal to 1. And this lemma told us GCD of Q prime is not to 1. And I will get contradictions that here alpha to the k is p over q. It's equal to mq prime over p prime over q prime from this equation. And then q will divide p prime minus q prime times p. And because the GCD of q and p are 1, so we can divide it. Then GCD q prime divide GCD p prime minus q prime and q prime. Q prime. And this is equal to 1. And which is a contradiction with this lemma.
And why the last is equal to 1?
Because q prime and q are coprime.
Q prime and yes, we assume that Q prime and
Yeah. And then we get, if we assume this equation, it gives a contradiction. So they are both not rationals. Okay, it's okay.
Okay. Fine.
And they are not rational to tell us that n the fractal part of n alpha to the L are belongs 0 to 1 and not equal. And alpha to the k minus 1 is also in 0, 1 because this inequality. So we get the following equations.
Yes. Okay.
Okay. Now let me show why we'll get the identity. This is the left hand side minus the right hand side. And first we open this bracket. It's an alpha L plus K minus the fractal parts and times alpha to K. And we minus the integer part of this, so we get the fractal part. And this equation is important. And then the third equation is because n alpha L plus K equal to n alpha to L plus mn. So they have the same fractal parts. And we can get the following equation. And here from the above equation, we say it's belongs to 0, 1, and here it belongs to minus 1 in 0. So the integer part of it is minus 1. So it's equal to 0. And we got the identities. And the important is to say alpha L is not rational.
Okay.
Okay.
Okay. So only if part becomes very easy, just one line.
Yeah. Okay.
I am, although this is very easy. I am a little bit from the very beginning when you prove this. It was a little bit disappointing. So I will ask Anton all the time. So Anton, is it okay? Is it okay for you?
Yes.
Okay.
I think all is okay.
Everything wonderful. So because we proved that this fraction, this alpha to L is irrational, then this thing is belong between minus 0, 1, because 1 minus alpha K is here. And this means that it is just minus 1.
Yeah.
Okay. Okay. So, and Zhuravlev had in the very beginning just only if part.
Yes.
Yes.
We found the identities.
Okay. Okay, let's continue. So
Let's continue.
if only if part is clear.
Yeah. Let's prove the if part. First, from this equation, it's equal to this, and we get if it's equal to 0, then we can get this equal to 0. So the fractal part of this is L. Okay, this is belongs to minus 1 to 0. So it's this equivalent. And so, and we if we write Fn be the point on the fractal part of n alpha L and n fractal part of n alpha to the L plus K. And we say the condition is equivalent to the point Fn belongs to a region S from this condition. The S is something like this. S is something like this. And we say that if this identity is equivalent to say that if we write F be all the orbit of the point, and the equation is equivalent to say F belongs to S. And if we regard F as a fundamental domain of a torus, and we say F is the point in the torus. Okay. And if one alpha to L plus K are linearly independent, and it's well known that the orbit is dense in the torus. That is, F is dense in the square. So it is S, but
it cannot belong to a part of a torus. Yes.
It's the F must have point outside the S. And then if they are linearly dependent, it's more interesting. And first, if alpha to L are rational, and it's easy to say the equality is wrong because we can take M be the denominator of alpha to the L, and the sum will be 0. Oh, maybe here will be 0. Or you can say from the equation, from this equation, it be 0 and this is greater than 0, and it's a contradiction. So we get alpha to the L are irrational, and by the linearly dependent, we say that alpha to L plus K can be write as S alpha to L plus R for some SR rationals. And now we claim that if F belongs to S, then we must have S equal to 1 and R equal to R belongs to integers. This means F is the diagonal in the square. This F. F is on the diagonal.
I think that the closure of F is a diagonal.
Oh yeah. But I mean that's F belongs to the diagonal. Yeah. And
Okay.
Okay.
No.
But well, why it happens that S is equal to 1?
What? S equal to 1 is the slope equal to diagonal. I will prove the connect.
We will show now this.
Yeah, it's just a connect right now. And by our assumption for alpha to the L are irrational and they are linearly dependent, then what will be the orbit? It will comes from the chronic wild theory. This is the orbit. From chronic and wild tells us the orbit of these things will be equidistributed in some paradigms. Will be equidistributed in some subtorus.
Yes, it belongs to a torus as a subtorus of smaller dimension.
Yeah, for one-dimensional subtorus. Yeah.
For one dimension, in our case, yes, one-dimensional subtorus.
Mm-hmm.
And it should be dense there because alpha is irrational.
Yeah. Well, one coordinate is irrational. Here is alpha to L is irrational. And for this theory, I can just give an example that if alpha square, if L equal K equal to 1, and if alpha square equal to alpha plus 1/2, then the S theta here is here theta is alpha plus 1/2, and S theta here is A1, A2, B, not A2 times Q, such that A1 times alpha plus A2 times alpha plus 1/2 equal to B. And this is A1 plus A2 alpha equal to B minus 1/2 A2. And because alpha is irrational by our assumption, so A1 must be, there must be 0. So S theta here is exactly some K minus K 1/2 of K, and the K is an integer. And the orbit will belongs to the C, belongs to C here is alpha x in R2, and it's minus kx plus 1 plus k x2 more 1 over 2k. And this is x1 plus x2 more 0, and b minus, so 1/2 more. If k is odd, it's the second one, and if k is even, it's the first torus. So this is this torus. First is here, and the second torus is this one. So for this case, the orbit is the two torus. And so if in here, if alpha is rational but not an integer, we can say there must be a subtory goes through the y-axis and will go into the left triangle. We'll go to the left triangle if it comes through the y-coordinate. If alpha is rational but not an integer, so it's a contradiction. Okay.
Okay.
And now we say alpha R is integer, so the torus will be from here, something like here. Go out here, and we can compute the coordinates that this is 1 over alpha to the k0. This is 1 over alpha to the k1. So the x coordinates are the same. And if if our subtory go into there, it will come out from this segment.
Yes, it is clear that so you have only you have only one subtorus, which if you consider all rational one-dimensional subtorus of two-dimensional torus, you have just only one subtorus which lies completely in the gray region.
Yes.
And this is just diagonal.
Yes,
Other subtorus cannot be covered by this gray region. This is the main explanation why the result is true. Again, the observation is very simple, that if we have a totally irrational vector, so the alpha to L and alpha to K are independent, then it is dense, and this is easy. So, but if they are not dense, they are dense in some subtory. And this region, which is determined by the condition on integer parts or on fractional parts, admit the following property: it does not intersect, it does not cover any other one-dimensional subtory, just only the diagonal. This is some I just have a question, two questions. First of all, Zhuravlev had many identities. So some of them or all of them be I don't know whom I ask this question. Can some of them or all of them be interpreted in such a way that there is a domain which does not contain other rational subtory, or maybe there is a general statement in the opposite direction. If we start with domain which doesn't contain subtory, then we can come to certain identity or something else. Can anybody say if there is some more general statement? This is a question. It may explain the nature of phenomena that we have a gray domain, and this gray domain can cover just one subtory. And this means, and if domain covers just one subtory, then belongingness to this domain ensure that we are in fact at this subtory. So it is something, some kind of explanation of the phenomenon, isn't it? So what Anton will say?
I don't know the answers.
But they may be easy. They may be, something may be clear.
If you have another equation and
I
maybe
have another remark. I think that this method obtains also the following. If we take some completely irrational vector, we can find a subsequence of n, which will be a linear graph, and such that all points lies only in F.
In F,
in gray area.
In gray area.
The gray area is S. Yeah, okay.
You mean, you mean linear growth in your meaning is not an arithmetic progression.
Yes.
It is something irregular.
Moreover, this subsequence will be depend on concrete vector.
Yes,
but it will show that this theorem cannot be generalized on an arbitrary subsequence.
Yeah, I think this set of such subsequences is very thin. So you can speak about small or zero Hausdorff dimension, I think, because they look like something say quasi-periodic, I think.
For special sequence, maybe it's not very. It's maybe hard to say.
I think it is possible to construct this sequence just by algorithm, but I think it is possible to prove that it is I cannot say strange, but something irregular. So it looks like some. I don't know. I don't know. So you see, we do not know. I have a feeling that there may be some interesting results, but I don't know how to formulate them.
No, I ask only about an existence of this sequence.
I think it is.
It is simple to prove that it exists. Of course, if we say that this subsequence can depend on vector.
I think it is clear. It should be clear that there is a sequence of positive density. Linear growth means something like positive density.
Yes.
That yes, and it will be and moreover, I have a feeling that it is possible to prove something about its structure. That it is so this set of examples is very thin.
Yeah, maybe if it's R, for example, it's S alpha beta depends on alpha beta, maybe irrational, or it maybe independent. If AK, maybe we can say that it's will depend. I'm not sure.
Well.
Maybe I don't know.
Okay.
Let's continue.
Yes. So everything up to now, I think everything is very clear. So
So here we have proved that alpha 2L plus K minus alpha L is an integer, right? It's what we prove.
Yes.
And then if the diagonal belongs to S, that means there will be some inequality that first alpha to the k it must be greater than 1. And the alpha to the k minus 1, kx is less than x. This line is below this one, this line, for x belongs to 0, 1. It's that the diagonal belongs to S. So from this we get the range of alpha to the k, and so alpha belongs to 1 and 2 to the 1 over k, and it's easy to say if alpha equal to 2 to the 1 over k, there must be something wrong. And from this inequality, we say they are in the interval. So we prove, and it's an integer. So we prove the if part.
So one moment. So so you did use that this belongs to the interval, and I missed the following thing.
Because the diagonal belongs to the S, so we have some inequalities. The first is this slope must be greater than 1.
Okay.
And the second is this line is below the diagonal.
Okay.
And we can get this inequalities. And if the here is equal,
Yes.
and there's a simple proof that it can't be true. And therefore the alpha.
I see. I just have again question about only if part. So, but if this difference belongs to the it may happen that it is not equal to 1, but belongs.
Yeah, maybe it 2. Yeah. What's the question?
But
sorry.
Here you're right. 2 to the power L over K.
Yeah.
And what did you deduce? I cannot compare it with if part. So one moment. So this happens if and only if. So if this belongs to the interval, then we prove this
identity
just by calculation.
Yeah, right.
And if the identity is true, then the diagonal should belong to this great part.
Yes.
And then this difference is integer, and we have the desired bound for this difference.
Yes.
Okay, fine. Let us continue.
Okay, then it's some generalization. The first part is, in fact, the generalization of Zhuralev's. Maybe they generalize these things. That's because here is one, and in fact we can take it some any delta belongs to all to one.
Yes, these two identities are equivalent.
Yeah.
Frankly speaking, they're equivalent.
So, if tau equal to the golden ratio, the identities will always hold if we take this is something delta here. And can say what's it? Oh. First we if delta equal to 1, it's the same as before. It's the same as theory 1.3. And here, if delta belongs to this region, and we can say that n it holds for all n, not only non-zero n. Because if we take it 0, it will be, this equation is always true.
Does I correctly understand that for delta equals to 1, this result is also true?
So, sorry?
Is this result also true for delta equals to 1?
Yes, but here, if our delta equal to 1, it's non-zero integers. Yeah.
You mean that for delta equals to 1, it is not true for n equals to 0, yes?
Yeah.
Thanks.
Yeah. And also, we assume alpha is not 1. And if alpha equal to 1, it's also true. And the proof of this theorem is this in fact S is something like this. Here is delta. And also we can prove that the diagonal must belongs to S. So this gives us a range of delta. And also it's a diagonal belongs to delta. And if it's so if it's the slope is not 1, it will go out the range. So everything is the same. Any questions? Is it clear?
It is likely that it is clear.
Okay, let's say the second generalization is if we take the equation here, we let the coefficient be m, not only 1. And there will also be an identity criterion for the alpha. And I just show the picture. And what we need is, the first is also the Fn is equidistributed. And the second, here S here m equal to 2 in the picture, and our s is something like -2 alpha x. Our s is here, and it can be divided by two regions. It's S1 is -2. Oh, it's -1. S2 is -2 less than y less than 1. Or less than -1. It's S1, S2. What we prove in our paper is the orbit will stay the same time in every region. That is Fn n for n less than big N. Fn belongs to Si over n. Limit is 1 over n. Here is 1 over 1/2 here. And then we say that in the picture, the blue one, it's the blue one makes S1 is much longer than it makes S2. So here the diagonal is not our choice. And what we need is a green one. They are equal in the region. And the red one will go out of the region. So it's just a sketch of proof. Did I say more?
Oh, please show the previous slide
Yeah.
with the theorem.
Mm-hmm.
So M here is fixed.
Yes.
You consider two successive powers, K and L, and now L and L plus 1.
Yeah.
And M here is fixed.
Here L and M are fixed. Maybe it can be improved by here is plus K, but we don't do it.
Okay, well, let us have a look then. Let us have a look then at the picture.
Yeah.
At the picture. So I did not understand well this argument with two parts of blue diagonal. So why this sequence should have the same frequency for these two intervals?
It's use equity distribution.
It should by uniform distribution the time of what this sequence spends in the first interval in the intersection with S1 should be proportional to the length, and which it spends in S2 should be proportional to another length. But why it is why in this setting you have equal frequencies for these two intervals? This to contradiction. I understand this, but I did not realize why. How do you get this contradiction? How do you explain that?
It's
frequencies are the same.
Let me save it. we consider the n m alpha to L minus m alpha L plus 1, and this is equal to 1 alpha L plus 1 minus 1 alpha L. It's an identity. Yeah. And in the left-hand side, we consider the point of alpha to n alpha L and m n alpha to L. And this will be in maybe if I need to write more. This is equal to m n alpha to L. Oh, and yeah, and minus n m alpha to L plus 1. This belongs to 1 to m intersects the integers. Okay.
Okay.
And if we let is Rn be the error, and Rn equal to J n number of it's over n is 1 over n should be. It should be. Yeah, for this point, let me say, because this point is only in the in these segments. The slope is m for this point. It's clear. Yeah.
On this picture which you have drawn now, you have m lines multiplied by m.
Because here x is this is x, this is y, and the y is equal to mx plus something maybe. Yeah.
So here trajectory always belongs.
Trajectory is clear for is m segment.
Yes, yes.
Okay. So if r equal to j is equal to say it's in the j segment, for r equal to j. Okay.
No, I don't understand the last formula. So what is written here? In the where equals 1 over m.
If Rn equal to j,
yeah,
means the point is on one of the segments, is on the j segment.
Okay.
And so they are equal distribution. So it's less than n. This over n.
Yes. Oh, this is n. This is n capital in the denominator. So
yeah. Okay,
I see. We devote the interval into equal. The trajectory into equal parts, and the parts are equal, so the distribution should be 1 over m.
Yes,
so
yeah.
The frequency for each of the parts should be 1 over m. Yes. And
and then if Rn equal to J means that the right hand side is equal to J, right?
Yes.
And it's equal to let me say what's it? So something like maybe I need more page. It's alpha L plus 1 minus alpha L alpha is alpha plus 1 minus alpha L plus 1 minus L alpha is the integer part of this minus alpha L alpha, okay. Right?
One moment. The last one. Where minus you put integer part inside another integer part. It is possible. And yes.
And this equal to J means it belongs to this maybe J plus 1 and J for this is let it be Sj.
Okay.
It means this for it let x equal to alpha to L, y is alpha L plus 1, and the slope is alpha. Yeah. Right? And so R equal to J means the point is belongs to Sj. So Fn belongs to Sj is equal to Rn equal to J. And because we proved before that Rj is this is equidistributed, so the Fn belongs to Sj is 1 over n. It's equal to what we proved before, and Rn belongs to Sj. Okay.
Okay.
So if you look at the blue one, it will stay longer time than states in S2.
So I see. It means that the coefficient for the subtorus P2. All other coefficients do not allow to have uniform distribution.
What is not why is not equidistribution? Yeah, it's the same. Yeah, right. So that just means the segments stay are equal length in Sj.
Asymptotically, the trajectory should stay equal
Mm-hmm.
time in each red segment.
Yes, in each.
No, I don't. I cannot. I cannot say it well. So in each. In each gray segment.
Yeah, the great one, because the green one, they are the this is in S1, this is in SJ, and they are the same length.
Yes.
So this is only a node case in this series.
So nevertheless, I did not understand well why they should stay the same time in S1, S2.
Let me repeat. Because the first, if Rn equal to J, right? Here,
you mean that the remainder is just J?
Yes. Yeah.
The remainder is just
remainder equal to J. They are the same length by equal distribution. By this here, this equal distribution. Because Rn equal to J is the same to say it's one of the segment it has length 1 over m.
Я тоже не очень был. Николай, можно я по-русски? Можно еще раз, почему вот как раз Rn равно J равномерно распределено по сегментам?
We do not understand. We do not understand why. We do not understand this asymptotic equality about the number of n's for which Rn is equal to J. Why it is equidistributed for different J? Why for different J we have the same asymptotics? We do not understand it well.
For Rn equal to J, it means that this n alpha L, m n alpha L here belongs to the J segment in here in this square in this. This is correct.
Rn is the difference of integer parts on the bottom of your slide. It can be written as a difference of fractional parts, and it belongs to the interval between 1 and m.
Yeah.
So,
yeah.
Yes. So if we specify the concrete value of Rn, why it is why then the point belong to the
segment.
First segment. Look, I think I understand. I think I understand. Look at the second equality for Rn. Rn is a linear combination of two fractional parts.
Yeah.
A fractional part is x and y. So we have mx minus y plus 1,
Yeah. It's belongs
which
to
is an integer, which is a fixed integer. It means that mx minus y is equal to something integer. It means that we have a shift of a line with coefficient m by an integer vector. And because of elements belongs to 0, 1, I mean x and y, fractional parts, then this shift is one of the segments which are surrounded by green on the picture on the right-hand side. Yes?
Yes. It's just if we say the lift, it's m. It's 1m the point, and if in one segment, it means that it's shifted by maybe if in this segment it means it's a shift by j.
So in fact, and after this observation, we see that the trajectory belongs to a very special subtorus with subtorus with coefficient m.
Right.
And we cannot, so is it true that now at this step we see this subtorus with coefficient m and the argument that it cannot lie on diagonal is not necessary?
Yeah, it can't be on the diagonal if m is not 1.
Why it can, if m is not 1, it is clear that it cannot be on the diagonal because it belongs to this m torus.
Yeah.
So you with m, when m is not equal 1, you simply should not speak about this diagonal on the next slide. So please show the next slide. So you should not speak about this blue diagonal because
Yes.
it is senseless because we know that the trajectory belongs to red lines. For instance, if m equal 2 or 3, m equal 3.
Equals 3. It will be outside the region.
You should not speak about this blue diagonal because it is not related to the argument, isn't it?
The blue one is considering this point, this orbit, and this contains in the blue one. Okay, in this theory, we use twice of this. The first is we considering the first is in the M segment, and the second is in the second is in SJ. Let me say. Oh, I know what. There's nowhere to write it. That's first Rn equal to J is the point n alpha L, and M n alpha L belongs to the J segment. And the second is Rn equal J is alpha 2L, and n alpha 2L plus 1 belongs to Sj. and there are two orbits, in fact, and in fact they are equal. They are the same.
Something unclear. Where these two orbits come from?
Because
two orbits.
I will write it first from the identity, and we write it in the left and equal to the right. Okay, we rewrite it. Have to say where's maybe I can write here. It's the identity is can write as m equal to n alpha l plus 1 minus n alpha l alpha. It's Rn. Okay.
If you consider the first equality, then you have one. You have.
If we consider the first, this means n alpha l and n m alpha l belongs to the J segment of
Yes.
mx j. Yeah. And if we consider the second one, it's m n alpha l and n alpha 2l plus 1. This is belongs to Sj. That means j plus 1 less than y minus alpha x less than j.
Okay.
Okay. From the first part, we know that if Rn equal to j, and we have n less than n, Rn equal to j over n is goes to 1 over m.
From uniform distribution.
Yeah. Because it's
I don't understand the last.
Yeah.
What is the last? The last.
Что Rn равно G равномерно распределено.
Sorry,
Я туплю.
Я тоже сегодня совсем не в форме. Oh, sorry. Today we had some problems, I think, but nevertheless, let us try to understand. Okay. So we have this the first. In the first case, we have two fractional parts, and they're dependent, but by irrationality, they are uniformly distributed in the torus of dependence. Dependence gives us a subtorus, and they're uniformly distributed in this subtorus. This subtorus, being cut by the initial torus, gives us m intervals. This subtorus, in fact, is a circle of a longer length.
With no for m. Yeah.
And this circle, and we have a sequence uniformly distributed in this. So this two-dimensional sequence can be interpreted at one-dimensional sequence as this circle of large length, which this circle of large length has m
segments.
Subintervals of equal length.
Yes.
Because of uniform distribution on the circle of large length, the frequency for each of subinterval is the same.
Yes.
Okay? Антон, лучше становится?
Не становится.
Okay, let me try to repeat. Давайте, I'm sorry, I will speak Russian for some time.
Okay.
I will repeat in Russian what is in English. So, у нас, вот, когда мы рассматриваем первое представление R как две дробные доли, эти дробные доли, они зависимы, значит, он принадлежит какой-то подрешетке, какому-то подтору одномерному. Okay, it belongs to one-dimensional torus. This vector AN belongs to one-dimensional, to factorized one-dimensional torus. Он принадлежит рациональной обмотке изначального тора. Правильно?
Вроде бы.
Значит, эта обмотка, это просто окружность. This is a circle. Это просто окружность. Если мы разрежем эту окружность на кусочки, то это вот мы получим вот эти вертикальные линии на зеленом квадратике.
Да.
Все они равной длины. Дальше, если у нас вот после введения новых координат вот эта двумерная последовательность будет одномерной последовательностью на длинном торе, она должна в каждой, поскольку она там-то равномерно распределена, по причине того, что она иррациональна, там все-таки не все альфа рациональны, то получается, что на каждом интервальчике она асимптотически одинаковое время должна проводить.
Это безусловно, только G это не номер интервальчика. G это номер сегмента, который с интервалами не очень понятно, как соотносится.
So this is a problem. Yes. What is J? So this is the problem. J is not. What is J in your?
J is a number of SJ of gray segment.
If you fix Rn equal to J, if you fix Rn equal to J,
yeah.
Why? This means that you consider fractional parts which belong to one segment. If you fix J, it means that you consider Sj from the second representation of R.
Yes.
Yeah.
I don't understand this moment.
You can write it more specifically. Say, here. Okay, the left-hand side is equal to m n alpha to L minus m n alpha to L plus 1. Right hand side is I forgot in this minus of the integer part of n alpha to L plus 1 minus n alpha to L times alpha. Okay. And this, if this equal to J, means n alpha L plus 1 minus n alpha L alpha is, yes. Maybe here J is minus J.
Okay.
that method. I mean, it's something this less than j minus 1. If we here j belongs to minus and 1 minus 1. Okay. And
if we replace two fractional parts by x and y,
it's
yes, then
so
we will have a domain on torus.
Yes. This is our SJ.
Yes, and xy belong between 0 and 1.
Yeah. It belongs to the 0, 1 square. Right.
Okay, this is so this means
and also it's if this equal to j, and then consider this is this is this. Maybe I can write n alpha L and n alpha L plus 1. Maybe I write this point is Gn, and this n alpha L mn alpha L, maybe write it Fn, and this is equal Gn in Sj, and it's equal Fn in the J segment.
Wait a moment. So so Gn is the xy's which satisfy from the second representation.
Yes.
When Gn belongs to Sj, it means that
so Rn is J.
From the first, that it means that Rn from the first representation, if we consider Rn from the first representation, it is the same value. It is equal to J.
Yes.
It is equal to J, and after rewriting it in fractional parts, after rewriting it in fractional parts, it is on the left part of the bottom. So Rn is equal n alpha L fractional part, and another fractional part nm alpha L. Okay.
Yeah.
This representation, you call it Fn.
Yes.
And if these now you consider the first representation, and in the first representation you claim that that Rn equal to J means that it belongs to the J segment of this line y equal mx plus J. Yes?
Yes.
Because can you explain this second part one more? So Fn
is from, let me see, from this is equal to mn alpha minus mn alpha to L plus 1. And the point Fn is this is x, this is
okay.
And so M
I will.
and
Anton is the main person to understand now. Антон, is it better? Стало лучше?
Я в процессе вспомнил, что я это проверял и что это правда, но сегодня я в это уже, видимо, не въеду.
Ой,
Я
понимаете,
тоже сутки не спал.
я сутки не спал, у нас потоп
Я
был.
тоже.
Курс мы сегодня отменим, потому что я вообще ничего не могу, понимаете?
Я в аналогичном состоянии.
Вот. Просто действительно я не спал сутки, я ничего не могу. Окей, sorry for our discussion. Okay. Well, so, but it seems to me that we have two representations, and it may be explained easily. So to have uniform distribution in SJs. So by the identity, belongingness to SJ,
yes,
is equivalent to belongingness to J's interval.
Yes, J's interval.
Because we have two representations of Rn. One represent due to identity. One representation is claims that XY belongs to SJ, and another representation claims that it happens if and only if F belongs to J's interval.
It seems that I understand. Yes.
Okay.
Thanks.
Okay. So, Anton, you said you tried to check it before and it was successful. So,
yes, I remember. It seems that now I understand the idea.
So the identity is equivalent that this gray segment, the gray segments cover the M torus, and they cover it properly. So the first segment, it's at the time. Also uniform they cover it with respect to uniform distribution. So J's segment should be covered by SJ.
Yes.
Because belongingness to SJ is equivalent to Rn. To equality Rn equal J, and it is equivalent to belongingness to M plus XJ interval, because we have two representations for Rn.
Yes.
Okay, probably we passed this place. It is something just which follow from identity.
Yes.
You should not speak about this blue diagonal.
Okay. Because
it identity in our case we have three. In the picture, we have three gray regions. You draw only two of them. And we have three, the number of gray regions corresponds is the same as the number of segments of the corresponding line. Isn't it?
I think that two segments is correct, but we interested in the green line, not in the red line.
Ah,
In this picture.
And not the red line.
we interested in green line.
Yes. So we have two regions here.
Okay. And green line corresponds to M equal 2.
Yes.
Yes. Yes.
Okay, so red lines and blue line are not good at this picture.
Yes.
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 They make it less clear.
The blue one means that Oh,
Okay.
The green line means that alpha L plus 1 minus M alpha JL is an integer. Here is 2.
Yes.
And this is only a not 1.
Okay.
Any questions?
I think we may continue.
Okay.
Yes.
So one more question to Anton. So you think this, Bohan, can you show once more the formulation of the theorem which we are discussing now? Once
Yes, this.
With this M, this is M theorem in to be the difference from the previous one. Then in previous one we did not have M different from 1, and here we have a different M. So the novelty is that M is not 1 here. Well, okay, I think that a general state. Okay, I will say a few words later. A few words later at the very end. So okay, let us continue.
For 1, they are the same. If M equal 1.
Okay. Yes. Well. Let us continue.
Yeah. And the third generalization is we can take the N to be the polynomials. And use Weyer's distribution for polynomials. We have the same segments of names. That is equal distribution. So,
yes. Let me say a few words. So it's a pity, but this construction does not give a result for Fibonacci sequences.
Yes.
So yes, it is a beautiful observation concerning uniform distribution, but it does not work with it does not involve enough arithmetics. Probably Fibonacci, to deal with Fibonacci and some other sequences, you need to consider some arithmetics. You need to consider decomposition into just something like Kastrovsky. I don't know what. But if you deal with some regular systems, regular sequences, such as polynomials, this method can be easily generalized, and we simply can, instead of n, we can apply it to arbitrary, roughly speaking, to arbitrary sequence, which is uniformly distributed on two-dimensional torus, and which sections by lower dimensional rational subspaces, or say, I don't know how to say, not projections, but sections on low dimensional subtori of this two-dimensional torus are also uniformly distributed. Such a model sequence is a polynomial sequence.
But for arbitrary sequence, I'm afraid something will be avoided, because you have two, for example, you have two, at least you have two subtori. If you have these two subtori, if the sequence is equally distributed in this, only in this diagonal, but not in the red one, it may be something wrong.
But I don't know. I don't know if sequence is uniform distributed. Then I think any. Is it true that any arithmetical, if we consider a subsequence enumerated by arithmetic progression, it will be also uniformly distributed? I think it follows from weight criterion.
Yes.
Then I'm not in arithmetic progressions, but not in I don't know. Well, now I'm sorry, I'm not too fresh to. Okay, let us. I think there is a lot of questions, but we should now. I mean, not just now, but now in this period of our life, we should stop somewhere. So.
Okay.
So let us deal with polynomials, and this will be a point to stop to look for the upshots, the results. Okay.
And for polynomials, in fact, we need some assumption for they are not rationals. And because if they are rationals, we have a counterexample. And for example, if the Pn is 4n plus 1, then alpha is the rational one can be also satisfies the identity, but it's not a solution of the.
Okay. Yes. One comment. In the previous results, you proved that from the equation, we have that from the condition we have alpha necessarily be irrational.
Yeah.
In your previous result, you start with the lemma, with coprimity lemma, which claims that alpha cannot be rational. Yes, cannot be rational.
Yeah.
And if we try to generalize to a polynomial case, we lose this property that alpha definitely is irrational.
Yes.
This gives a contradiction. Am I right?
Here, polynomials, it's
Okay, this is just the example.
Yeah, it's from the identity. It can be not. It can be rational.
Identity is satisfied, but alpha can be rational.
Yes.
This is an opportunity to for theorem for the statement not to be true.
Yes. So we need this assumption.
Okay. Okay, fine. So, well, then, so new assumption is that both of them are irrational.
In fact, one of them are irrational, and we can.
One of them, just one of them is enough.
Yeah.
Well, okay. Of course, it should be. Okay, now I think you did not you did not have a plan to speak about the proof of this, as far as I understand. Yes.
Yeah, but because the
I think what is obvious.
What is obvious?
Oh, this theorem.
This theorem, in your opinion, Anton, this theorem is obvious.
Yes.
After previous theorems, this is okay.
Yes.
One.
But red part is very surprising.
I think this example should be mentioned because it is easy and it shows something. Okay, wonderful. Okay, let us continue.
And then it's just an open question that if we take more brackets, can this be true for algebra integers?
This is a problem which look. Oh yes, it is very wonderful. So it is very nice that we organized this seminar, this presentation with discussion, because when you are listening to discussion, you have much more ideas than when you, sometimes than when you are reading or doing something else, so discussing just one by one. So public discussion makes something sometimes something more clear. So, and I want to say, I don't know how to say it. If I have a new idea or something else, I want to note one observation, which is, I think, which is related to everything here, including this problem. It seems to me, why just few words about this problem.
Yeah.
In your previous text, you were able easily to deal with the problem when these things are independent, because they cover the whole torus, and this is not possible. I think that the nature, and but you were not able to do with dependence case. I think that the nature of the problem is just related to the dependent case. Look, because what we are doing everywhere, from some bounds, that fractional part is less than 1, greater than 0 and less than 1, from identities, we deduce a region where XY two-dimensional point should lie.
Yes.
Well, and the only opportunity to lie in this region is that some rational subtorus is completely covered by this region.
Yes.
I think that this is a key observation, and this construction gives an answer to give all the answers to all the problems which can arrive here in this setting. Because look,
Parts, yeah.
if we have everything becomes much clearer. If we have restrictions, if you know that something on torus, maybe not on two-dimensional torus, I think there's five-dimensional results, but one comment. If something belongs to some bounded region, not to the whole torus, it should cover something of smaller dimension. If the set has geometry which does not cover anything, that it cannot happen. So, and the main problem is to, I do not speak about subsequences. Subsequences, such as Fibonacci sequences, include and probably include some extra arithmetics, which is not clear. But this setting is clear, so you have in the domain, this domain covers only very specific subtori, and this gives the characterization. So this is very clear. Another thing that when we deal with this identity with few brackets, then it looks beautiful. So if you try to I don't know if what will happen if you try to find a general statement. Maybe it will be not beautiful. I don't know.
It's very complicated.
Okay, but nevertheless, as for me, we get some more clarity now. Thank you very much. So,
Thank you.
So any other comments, questions?
Can you prove only if patch in problem 3-4?
In this problem?
Only if patch for some alpha.
But I
if alpha is a cubic root of 3, then all these are true. All these identities are true.
Sure.
I guess this may be a good offer to say Zhuravlev's birthday. Isn't it?
Maybe I can't do it. I don't know what I don't know what is the alpha in fact. Maybe the I don't know if there exists this kind of alpha.
So you do not know any if parts. Maybe not this identity, but something. Because I think Zhuravlev has enormous amount of if statements.
I remember something like this, but something like this.
You tried.
But I don't know.
But you don't. Okay. It doesn't matter. So well. Okay. So thank you very much. I think so. But well. I think we should discuss our plans. But I think that we can consider that our seminar now is over, and we can stop recording. Yes.
Yeah.
Okay. So no more. I think we will do not have no more public discussion. So thank you very much. It was really interesting. Well, and now we have a break.